Dear students, here we are going to discuss about the topic analysis of Brayton cycle. First of all, let us see the components of a closed cycle gas turbine unit. The main components are compressor, heat exchanger or combustion chamber, turbine and the second heat exchanger. In the compressor, the working fluid is compressed to high temperature and pressure, and in the heat exchanger, heat is added at a constant pressure to the working fluid. That is in heat exchanger 1. Then the high temperature hot gas enters the turbine and the gas expands in the turbine, producing mechanical work output. After performing work in the turbine, the working fluid enters the heat exchanger 2, and heat is removed from the working fluid and again it is fed to the compressor. This completes one cycle of operation. Now we are going to discuss the ideal cycle of a gas turbine unit. The working cycle of gas turbine unit is called Brayton cycle. It is also called Joule cycle. The main assumptions in the analysis are: first one, the working fluid is air and considered as ideal gas. Second one, the actual combustion process in the combustion chamber is replaced by constant pressure heat addition from external source. Third one, the exhaust process is replaced by a constant pressure heat rejection in a heat exchanger. Fourth one, the compression process in the compressor and expansion in the turbine are isentropic. That is, we are assuming the compression and expansion process are reversible adiabatic process. That is, no friction is involved. Now we can see the TS diagram of Brayton cycle. The first component of gas turbine unit is compressor and the compression process is assumed as isentropic. The process 1 to indicate the process in the compressor, that is isentropic compression of air in the compressor. The second component is heat exchanger, in which heat is added at a constant pressure, that is the process 2, 3 indicate the process in the combustion chamber. Now process 3, 4, it is the isentropic expansion of air in the turbine. This is the process that is happening in the turbine. Since it is isentropic, it is a vertical line in TS diagram. Process 4.1 is constant pressure heat rejection from the air. That is the process that is happening in the heat exchanger 2. This is the TS diagram of Brayton cycle. Now we can see the PV diagram of Brayton cycle. Process 1-2 is isentropic compression in the compressor. During compression, its pressure increases and volume decreases. Now process 2-3 is constant pressure heat addition in the combustion chamber. Since it is a constant pressure process, it appears as horizontal line in PV diagram. Now process 3-4 is isentropic expansion in the turbine, and process 4.1 is constant pressure heat rejection. This is the PV diagram of Brayton cycle. Now we can find out the expression for thermal efficiency of Brayton cycle. Efficiency of any thermodynamic cycle is given by the expression net work output divided by heat input, that is eta Brayton is equal to W net by Qin. The net work output can be found out as the difference between heat supplied and heat rejected, that is W net is equal to Q in minus Q out, or eta Brayton can be written as is equal to 1 minus Q out by Q in. Heat is supplied during the process 2-3, that is Q in occur during the process 2-3 and heat rejection occur during the process 4-1. Now heat supplied during the process 2-3 per unit mass of air, that is Q in is equal to H3 minus H2 is equal to Cp into T3 minus T2. We can write H is equal to Cpt because we are assuming the working fluid as ideal gas. Now heat rejected during the process 4-1 per unit mass of air, Q out is equal to H4 minus H1 is equal to Cp into T4 minus T1. Now substituting in the equation of efficiency, eta Brayton is equal to 1 minus Q out by Qn is equal to 1 minus expression for Q out is Cp into T4 minus T1 and expression for Q in is Cp into T3 minus T2. Cancelling Cp, we get eta Brayton is equal to 1 minus T4 minus T1 by T3 minus T2. Numbering it as 1. Now we can define pressure ratio. Pressure ratio Rp is equal to P2 divided by P1 is equal to P3 by P4. Pressure 2 and 3 are same since the heat is added at a constant pressure, and pressure 4 and 1 are same since the heat rejection is occurring at a constant pressure, that is P2 is equal to P3 and P4 is equal to P1. Now we need to find out the expression to T3 and T2. Now consider the process isentropic compression process 1-2. This is the isentropic compression process 1-2. Applying adiabatic relation to process 1-2, we will get P1 by T1 raised to gamma by gamma minus 1 is equal to P2 by T2 raised to gamma by gamma minus 1. From that we can write T2 by T1 is equal to P2 by P1 raised to gamma by gamma minus P2 by P1 raised to gamma minus 1 by gamma, or T2 is equal to T1 into Rp raised to gamma minus 1 by gamma. Rp is pressure ratio, naming it as equation A. Now consider isentropic process 3-4. For that, applying adiabatic relation, P3 by T3 raised to gamma by gamma minus 1 is equal to P4 by T4 raised to gamma by gamma minus 1. Or we can write T3 by T4 is equal to P3 by P4 raised to gamma minus 1 by gamma. Or T3 is equal to T4 into Rp raised to gamma minus 1 by gamma, naming it as equation B. Now substituting equation A and B in equation 1, we get eta Brayton is equal to 1 minus T4 minus T1 divided by T4 into Rp raised to gamma minus 1 by gamma minus T1 into Rp raised to gamma minus 1 by gamma. Now taking out Rp raised to gamma minus 1 by gamma, we will get the equation eta Brayton is equal to 1 minus T4 minus T1 divided by Rp raised to gamma minus 1 by gamma into T4 minus T1. Now cancelling T4 minus T1, we will get the final expression for Brayton efficiency of Brayton cycle as eta Brayton is equal to 1 minus 1 by Rp raised to gamma minus 1 by gamma. This is the equation for thermal efficiency of Brayton cycle. Now we need to define two terms. The first one is work ratio. It is defined as the ratio of net work of the plant to the turbine work, that is RW is equal to net work output divided by turbine work. The net work output can be found out by the expression WT minus WC, that is turbine is the work producing device and compressor is the work consuming device. A part of the work produced by the turbine is used to run the compressor. Thus, net work output is the difference between turbine work and compressor work. Now, the turbine work can be found out by the expression Cp into T3 minus T4, and compressor work can be found out Wc is equal to Cp into T2 minus T1. The second term is back work ratio. It is defined as a ratio of work input to the compressor to the work produced by the turbine. That is RBW is equal to compressor work divided by turbine work. Now we can see the expression for optimum pressure ratio for maximum specific work output. That is the pressure ratio which gives the maximum work output. For an ideal Brayton cycle, the net work output per kilogram of air is given by W net is equal to W turbine minus W compressor. That is, turbine work can be found out by Cp into T3 minus T4. This is the process in turbine. And compressor work can be found out by Cp into T2 minus T1. This is the process indicated that is happening in compressor indicated on TS diagram. Now taking Cp here outside, T3 here outside, W net is equal to Cp into T3 into 1 minus T4 by T3, and here taking T1 outside, we will get T2 by T1 minus 1. In case of gas turbine, T1 that is atmospheric temperature and T3 is the turbine inlet temperature. These two are the limiting temperature and which affects the thermal efficiency. Thus, expressing T2 and T4 in terms of T1 and T3, we get T2 by T1 is equal to T3 by T4 is equal to Rp raised to gamma minus 1 by gamma. This relation is already discussed in the derivation of thermal efficiency of Brayton cycle, where Rp is equal to pressure ratio is equal to P2 by P1 is equal to P3 by P4. Now using notation K is equal to gamma minus 1 by gamma, we will get W net is equal to Cp into T3 into 1 minus T4 by T3 minus T1 into T2 by T1 minus 1. Now substituting for T and T2 by T1, this equation 1 can be written as W net is equal to Cp into T3 into 1 minus 1 by Rp raised to K minus T1 into Rp raised to K minus 1. Now differentiating the equation with respect to Rp and equating to 0, that is differentiating this equation with respect to Rp and equating to 0 to find the pressure ratio corresponding to maximum work output. Now the first term, it is a constant, and the second term is T3 into 1 by Rp raised to K. Differentiating this term with respect to Rp, we will get T3 into K by Rp raised to K plus 1, and this term T1 into Rp raised to K, differentiating this with respect to Rp, we will get T1 into K into Rp raised to K minus 1. Now rearranging the terms, we will get T3 into K by Rp raised to K plus 1 is equal to T1 into K into Rp raised to K minus 1. Again rearranging and cancelling the common terms, we will get T3 by T1 is equal to Rp raised to 2K. Now substituting for K, we will get T3 by T1 is equal to Rp raised to 2 into gamma minus 1 by gamma, or optimum pressure ratio Rp is equal to T3 by T1 raised to gamma by 2 into gamma minus 1. This is the pressure ratio which gives maximum specific work output.